Now that we understand resonance a little bit, let's see how we use resonance in electronic circuits. So here's a typical RLC circuit, and when you're building a circuit like this, right, usually you have there's some sort of external voltage here that provides some sort of input to the system, some sort of signal that you want to process. Typical sources for this sort of signal are a wire. Maybe you're hooking your circuit up to a wire, or maybe you're hooking your circuit up to an antenna. Right. What an antenna does is, right, the electromagnetic field of the radio waves hits the electrons in the wire in the antenna and makes them move around a little bit, and that generates a voltage. And if typically that voltage is very small, and also typically that voltage is a mixture of many different frequencies. And somehow we need to arrange for this circuit to choose and amplify just one of those many frequencies. So to represent this situation, what we're going to do is write down a differential equation with a forcing function that has a particular form. So for an RLC circuit like this, the differential equation you get is inductance times Q double prime plus resistance times Q prime plus 1 over C times Q equals, and then what I'm going to write, the signal coming from the antenna is what shows up on the right-hand side here. And what I'm going to choose for this signal is just two different sinusoids with the same amplitude, but different frequencies. So we'll call the first one gamma 1, and the second one we'll call gamma 2. And gamma 1 and gamma 2, let's assume that they're very different. They aren't very close to each other. Okay, so our goal here is to choose electrical components so that we select just the first of these these two sinusoids, so that we can listen to just what this part of the signal is transmitting. Okay, well, since we're just listening, we don't get to choose what this signal is. All we get to choose is the circuit components. So it turns out that we can just choose a single inductor, so let's make it 1. The resistance in this circuit, typically you want it to be very small, because if you have resistance, you're just sort of wasting energy. So I'm just going to write small right here. And we're going to pretend that it's 0. It's not actually 0, but it's going to be very, very small. Plus 1 over C times Q equals sine gamma 1t plus sine gamma 2t. Okay, and what you can do is, in your circuit, right, you can choose a capacitor that's variable. So we can choose any value, we can arrange for this capacitor to be adjustable somehow so that we can actually change its capacitance on the fly. Now, if you, the way we have this set up, the characteristic equation for the associated homogeneous, I need a second prime here. The characteristic equation for the associated homogeneous equation is R squared plus, I'm going to neglect this small resistance term, plus 1 over C, and so R is equals 0, and so R is going to be plus or minus 1 over C times I. And so omega, right, the frequency of the natural angular frequency of this system is 1 over C. Okay, so you can see by changing C, we can change the natural frequency of this circuit. And remember, the natural frequency is the frequency at which resonance occurs. So if we choose, or if we set our capacitor to be 1 over gamma 1, then omega is gamma 1. And so when so our particular solution in this case will have a large amplitude. We'll get a resonance for the first signal, so it will have large amplitude. But then remember, when the frequency of your forcing is not close to the frequency, the natural frequency of the system, you don't get resonance, and so the response to this second frequency will have only a small amplitude. So times sine of gamma 2t. Okay. And what you can do then is sort of hook up some other output around your capacitor to listen to the resulting signal. In other words, the resulting y sub p. This might be maybe a speaker. Right. So if you set this capacitor to be 1 over gamma 1, then the signal at frequency gamma 1 gets amplified because of resonance. The signal at frequency gamma 2 gets suppressed, and you can listen to the signal on frequency gamma 1. Of course, if you want to instead listen to the frequency of gamma 2, remember that this capacitor was variable, and so we can, if we want to listen to gamma 2, we can change the setting on our capacitor, change it to be 1 over gamma 2. That produces a natural frequency of gamma 2, and then the particular solution will have a small amplitude for this portion of the signal at frequency gamma 1, and it will have a large amplitude at the portion of the signal that's at frequency gamma 2. So just by changing this capacitor, we can listen to one signal or the other signal and filter out the frequency that we don't want. So this is actually how radios work. I mean, it's a little more complicated than this. There's more electronics involved, but this is the basic principle that lets radios be tunable. You have some sort of variable circuit component, sometimes a capacitor, or sometimes it's the inductor that's variable. But you change the value of that circuit component to make the resonance frequency equal to the portion of the signal that you want to listen to.